Failures by wear are not usually considered as serious as failures involving fracture. This is because failures by wear are not typically catastrophic. Wear is just something we have to live with and usually accept as perfectly normal. Our shoes wear out, our clothes, our tires, appliances, cars, machines, everything seems subject to wear. Though not as catastrophic as fracture, wear can play serious havoc with the pocketbook, given the cost of replacing worn parts, resurfacing the old, and repairing the damage that wear can cause. So many industries exist solely to replace worn-out parts that if all wear were suddenly eliminated, the impact would devastate the economy of all industrialized nations. But of course, wear can never be eliminated, only minimized. Two factors are closely allied with wear in affecting the tendency of parts to fail, or at least to cease being able to perform: friction and lubrication. All three elements, friction, lubrication, and wear, are interwoven into complex systems that lead to failure. All three elements are extremely important, but only wear will be emphasized in this program. Friction and lubrication are discussed only as they relate to wear. Tribology, the science of wear. The term tribology comes from the Greek word tribos, meaning wear. The science of tribology actually involves the mechanisms of friction, lubrication, and wear on interacting surfaces that are in relative motion. Wear itself is generally defined as the undesired removal or displacement of material from a surface, primarily by mechanical action of a contacting solid, liquid, or gas. A gradual deterioration of the surface is usually implied. The effects of material removal, displacement, or gradual deterioration are generally limited to surface or near-surface related phenomena. However, during failure analysis, these restrictions should not be rigorously applied. Nor should wear be accepted as an entirely mechanical problem. Very often, at least two different types of wear exist in any given situation. And the several types of wear involved may frequently be complicated by corrosion or fatigue, or both corrosion and fatigue. Also, wear is not always considered bad. Certain types of material removal from a surface by mechanical action are desirable. The mild wear, referred to as breaking in or wearing in during the early operation of a machine, actually does some good. This wear to break in an automobile engine, for instance, removes slight projections from surfaces, permitting larger lubricated contact areas to exist, hopefully with little or no additional wear for long periods of time afterwards. In general, failures by wear are difficult to describe and to analyze and to prevent. Types of wear. Various types of wear can be described in several different ways, but there has never even been general agreement as to the types or forms of wear that may exist. One relatively simple way to classify wear is by the mechanical surface damage it causes. There are four major types: abrasive, adhesive, contact stress fatigue, and corrosive. These four basic types of wear are still not clearly defined because they tend to blend with each other and combine with different modes of failure. Abrasive wear can be defined as cutting. Cutting wear, in turn, can be described as erosive, grinding, or gouging wear. Adhesive wear is often called galling or seizing. It is defined as micro-welding, which can be either dynamic or static. Contact stress fatigue. This is defined as pitting fatigue. It is also described as cavitation pitting, which is caused by the formation and instantaneous collapse of tiny voids or cavities in a liquid impinging on a part. Contact stress fatigue can be further defined as subsurface in origin, surface in origin, or subcase in origin. Corrosive wear is simply corrosion combined with wear. This classification of wear is a convenient framework to organize the complex study of wear failures. Abrasive wear. The principal mechanism of abrasive wear is cutting. Erosion, grinding, and gouging all involve cutting by another material rolling or sliding across the metal under pressure at some velocity. Erosive wear occurs when low-stress, high-speed particles impinge on a surface at an angle. The particles tend to cut away very small chips. Erosion is a particular problem with various types of impellers, propellers, fans, and other parts where particles in the air, water, or other fluid strike the surface of the metal. Probably the best example of erosion is the Grand Canyon in Arizona. That is true erosion. In certain cases, the fluid itself, such as water or steam droplets, can be the eroding material. The very large number of very small particles tends to cause channeling, forming grooves, and removing soft surface layers. Erosive wear also tends to round sharp edges of various types of parts. Rounding edges reduces efficiency and eventually leads to complete destruction. In general, erosive wear can be resisted by increasing the hardness of the surface. This is frequently done by adding a relatively thick, hard facing or a relatively thin, hard, wear-resistant coating. It may not be desirable to increase the general hardness of the metal to resist wear by erosion, since a harder metal can lead to brittle fracture. The resulting fracture can be a worse problem than the erosive wear. Grinding wear results when high-stress, low-speed particles or projections from hard materials cut and plow small grooves in softer materials. This type of wear is characteristic of the damage to many tools in contact with the ground. Plows, shovels, cultivators, and other digging-type tools rub against hard abrasive materials all the time, and this grinding abrasion can lead to complete or partial failure and destruction of the part. Cutting tools particularly are badly dulled by grinding wear, yet some cutting tools can be made to be self-sharpening. The replaceable teeth of a power shovel, for instance, can be self-sharpening by making the cutting surface hard and the support surface soft. If the teeth were hard-surfaced on both sides, they would be dulled by the grinding wear. But a self-sharpening tooth, hard-surfaced on one side, wears away faster on the soft side. The tooth remains sharp and useful much longer. Gouging wear is difficult to recognize, except by knowledge of the application. In service, the force of gouging is usually very severe, high stress and high impact. The ripper teeth that are dragged behind crawler tractors are used to shatter layers of rock, and the rock in turn cuts and gouges the metal. Mining equipment is subject to this kind of severe service. Fortunately, a specific type of steel was invented many years ago that handles these applications well. Hadfield steel contains high carbon and very high manganese. It is an austenitic steel, extremely tough and resistant to high impact, high stress, battering types of service, but not to other types of wear. It cannot be machined easily, therefore it is usually cast or welded as a hard surfacing alloy. Adhesive wear. The principal mechanism of adhesive wear is micro-welding. This is similar to friction welding, but on a micro scale, at least initially. Both friction welding and micro-welding involve a welding action between two metals that are mutually soluble. That is, they are inherently capable of being welded together. Since adhesive wear is basically a lubrication problem, a lubricant, or perhaps we should say the lack of a lubricant, is frequently involved. Dynamic adhesive wear is frequently described in less accurate terms as scoring, scuffing, seizing, or galling. The actual mechanism is best described simply as adhesive wear. The term dynamic refers to the movement of one surface sliding past another surface. For example, a shaft rotating in a sleeve bearing, or two gear teeth moving and contacting under load. Adhesion is favored by chemically clean surfaces, non-oxidizing conditions, and by chemical and structural similarities between the sliding couple. The reason for this can be seen at very high magnification. The two contacting surfaces might look something like this. Projections extend from each surface. These are called asperities. And as the two surfaces slide across each other, the asperities from one surface tend to interfere with those of the other surface. Micro-welding occurs, initially at the very small areas where the peaks of the asperities contact momentarily. They are then torn or fractured from one surface, usually from the weaker of the two metals, if they are different. If a poor lubricant is present at the interface, the adhesion between the two surfaces escalates rapidly. The result? Gross overheating, and quite possibly large wear scars. In some cases, complete destruction of the surfaces may occur. For destruction of steel surfaces, the local temperature at the interface must range from 1600 to 2000 degrees Fahrenheit or higher. Hardened steels are quite sensitive at these temperatures, and great changes can occur in the microstructure. Rehardening will occur with the formation of very hard, brittle, untempered martensite at the surface, surrounded by softer, highly tempered martensite below the surface. The structure has a pattern quite similar to a grinding burn. To prevent adhesive wear, several things must be done. Keep bulk lubricant temperatures cool. This prevents overheating from contacting surfaces. Form relatively smooth surfaces. This keeps the asperities from penetrating the lubricant film. The lubricant should have viscosity as high as possible for the application. Coat surfaces with oil additives or coatings that form chemical films to prevent metal-to-metal contact. Use mutually insoluble metals with low shear strength. Gold or silver plating is sometimes used on one of two mating high-speed gears or other contacting parts to prevent adhesion. The other form of adhesive wear, static adhesive wear, is commonly called fretting. It has also been called fretting corrosion, friction oxidation, chafing fatigue, and wear oxidation. Instead of a dynamic sliding motion, static fretting involves adhesive wear in a joint that is essentially stationary. It is the very minute vibration that inevitably occurs during machine operation that causes a small elastic motion between the parts. The joint is supposed to be stationary or static, but actually it is not. A minute metal-to-metal rubbing motion exists at the interface, and this causes fretting. Static adhesive wear proceeds in much the same way as the dynamic. Again, micro-welding occurs. Tiny fragments are torn from one or both surfaces. The fragments oxidize to form a reddish-brown cocoa on iron and steel. This is actually iron oxide. On aluminum, the oxide appears as a black powder. The actual fretting is caused by the wear debris that oxidizes when exposed to air. This may also be called fretting corrosion. The so-called corrosion seems to be incidental to the wear resulting from the adhesion. One of the major problems with fretting is not the destruction of the joint itself, but the fact that it frequently leads to fatigue cracks and fracture originating at the interface. In many cases, the site where the fretting fatigue originates is different from the expected location of fracture. This is particularly true if the expected failure location has been strengthened by heat treating or mechanical pre-stressing of the surface. This steel spline shaft shows a typical fatigue fracture resulting from fretting on the surface. Several cracks occurred at the surface. Two of these cracks led to the final fracture. The dark material is the brownish-black corrosion product characteristic of fretting on steel. Fretting is not easy to prevent. It can be minimized, however, by one or several procedures. Using pads, gaskets, or bushings to absorb vibration. Increasing surface hardness. Increasing the hardness of one or both surfaces increases the resistance to microfracture. Chromium plating one surface. This reduces the coefficient of friction and helps prevent micro-welding. Mechanically pre-stressing the surface. Shot peening is one method. This helps prevent the fretting from causing fatigue cracking and fracture. increasing the movement of a lubricated joint. This allows lubricant to enter the interface between the parts. Contact stress fatigue. The wear resulting from contact stress fatigue is generally described as pitting fatigue. The pitting originates primarily on or near the contacting surfaces of ball and roller bearings, roller cams, and gear teeth. Because this occurs on or near the surface, there can be four types of pitting fatigue: subsurface origin, surface origin, subcase origin, and the fourth type of pitting fatigue is by the cavitation of liquids. Although the cause of the fatigue and the locations of the origins are somewhat different in each of these types, the fractures that can result are true fatigue fractures. They are caused by shear stress origins due to repetitive contact stresses between two metal surfaces or between a surface and a liquid. The common thread linking these four types of contact stress fatigue is that each represents the limit of load carrying capacity. Improvements are made only with great difficulty, if at all, assuming the materials and geometries are accurate. The ways to prevent the pitting differ with each type. Subsurface origin pitting occurs where one surface rolls under pressure across another and destroys the integrity of the contact surface between them. This is typical of anti-friction bearings, such as ball, roller, tapered roller, and needle bearings, as well as other rolling devices, such as roller cams. Under conditions of pure or nearly pure rolling, the maximum shear stresses are a very small distance below each of the two contacting surfaces. The depth of the maximum shear stress is on the order of a few thousandths of an inch, depending on the geometries of the contacting parts. Because the maximum shear stress is slightly below the surface in pure rolling, this is where fatigue fracture is most likely to originate. The fatigue tends to originate, however, at an internal stress concentration, at a hard angular inclusion, for instance, that will inevitably be present in the metal. A small piece of metal will pull out, and being hard and brittle, the piece is free to cause further damage as a wear particle. Prevention methods for subsurface origin pitting should be obvious. Eliminate the hard, brittle, angular inclusions by improved steel quality. This is a principal application for vacuum-treated steels, used in the manufacture of anti-friction bearings and other critical parts. Actually, with the use of vacuum-treated steels, failure by subsurface origin pitting is fairly rare. Surface origin pitting is characteristic of combined rolling and sliding. This is the action that occurs on gear teeth. On gear teeth, the pitting occurs slightly away from the exact pitch line, where only rolling is present. Cam and cam follower assemblies may also suffer this type of failure on the cam follower itself. Because of the friction at the interface, the maximum shear stress is no longer buried within the metal. The stress is brought to the surface. And because the character of the surface is intimately involved, the lubricant becomes critical. For this reason, various types of gear systems, such as transmissions and final drives, require lubricants with special additives. Sliding between the parts introduces frictional forces that may cause adhesive wear as well as surface pitting. The sliding tends to drag each surface in the direction of the sliding. This is in the opposite direction on each surface. Continued contact with the mating part causes small diagonal fatigue cracks to start at the surface and progress downward into the metal at an angle of approximately 20 to 25 degrees. The angle between the crack and the surface always points in the direction of sliding. With continued service, the crack progresses down into the metal a few thousandths of an inch. It spreads out on the surface until a small volume of metal has been surrounded by cracks. This cracked section soon falls out, leaving an arrowhead-shaped cavity or pit. This is a typical arrowhead-shaped pit in a test roller before it is destroyed by continued contact with the mating roller. Prevention of surface origin pitting is not easy. It represents the limit of load-carrying capacity of hardened steels. Everything possible must be done to reduce surface friction, expand the contact area, and reduce the load. The object is to reduce the contact stress and provide a hard, fatigue-resistant structure in the metal. An effective lubrication system is very important in reducing the contact stress. Unfortunately, if the surface friction contact areas and the loads are near optimum, little can be done to improve the fatigue life. Only minimal improvements, if any, can be expected. Sub-case origin fatigue is sometimes called spalling or case crushing. This type of contact stress fatigue can occur only on case-hardened steels, and the depth of the case is a major factor. Other types of contact stress fatigue result in small pits in the contacting surfaces, often very tiny pits. Sub-case origin fatigue is different because the small pits may form very large cavities, apparently in a very short time. The fatigue originates near the case-core interface, where the shear stresses, which are still fairly high, exceed the strength of the relatively low-strength core metal in that region. Fatigue cracks propagate parallel to the surface, but underneath the case. These cracks join and form cracks that come up through the case to the surface. The cracks are somewhat similar to those of subsurface origin pitting. Subcase fatigue cracks, however, are much deeper. Probably the only good thing about subcase origin fatigue failure is that it is relatively easy to prevent. The basic cause is inadequate metal strength in the subcase region. Logically, the solution should be to strengthen the metal in that region. This can be done by increasing the case depth, the core hardness, or both the case depth and the core hardness. This must be done carefully. Changes in case depth or core hardness can lead to through hardening and brittle fracture, particularly on gear teeth. Cavitation pitting is sometimes called cavitation corrosion or cavitation erosion. This type of contact stress fatigue is unique because only one metal surface is involved. The other surface material is a liquid, frequently water or water antifreeze. Cavitation pitting is caused by rapid, repetitive, relative movement between the metal and the liquid. When the metal and liquid momentarily move in opposite directions, the local pressure is reduced. This causes small cavities to form in the liquid at the interface with the metal. Then, when the metal and the liquid reverse direction and move toward each other, the cavities at the interface implode or collapse on the metal surface. The force of these implosions causes very high local contact stresses. If vibration or other relative movement is continued at these local points for a large number of load applications, the repetitive implosion forces cause fatigue fracture or pits to form in the metal surface. Cylinder sleeves, turbines, nozzles, impellers, any parts that move rapidly through a liquid tend to pit by cavitation. The high-speed flow of liquid in these devices causes local hydrodynamic pressures to vary widely and rapidly. The resulting pits can be quite small or very large and deep, depending on the particular circumstances. Continued service can cause complete penetration of the metal. One of the characteristics of cavitation pitting is that pitting occurs primarily in a pattern. Most of the pits are concentrated in specific areas, depending upon the local vibration or flow characteristics. Cavitation pitting of wet cylinder sleeves can cause complete destruction of the engine if coolant gets into a combustion chamber. Corrosion can easily occur on fresh, unprotected metal fracture surfaces, but any corrosion is incidental to the pitting fatigue that causes the pits. As might be suspected, cavitation pitting is not easily prevented. The reason is that vibration and liquid flow characteristics are not easily controlled. Streamlining the flow or adding a device to de-aerate the liquid involved offers good potential for reducing or eliminating cavitation. Corrosive wear. This is not really a separate type of wear. Corrosive wear is simply a combination of corrosion and wear occurring either alternately or simultaneously. Corrosion is a major cause of wear in automotive engines, particularly if the engine is stopped before it has had a chance to heat up to operating temperature. The moisture formed as a product of combustion at the startup cannot evaporate from the cold engine. If the engine is shut off cold, the moisture remains inside and condenses on various internal parts. Corrosion may occur if the lubricant does not prevent it. It is particularly difficult to prevent wear on parts operating in a corrosive environment, primarily because of the difficulties in specifying and testing alternative metals. Various types of surface coatings are frequently of great help in solving the problems of corrosive wear. Hard chromium plate is often used for corrosion and wear resistance. Titanium nitride coatings are used because of their hardness, coefficient of friction, and chemical properties. Summary: types of wear. Wear is generally defined as the undesired removal or displacement of material from a surface, primarily by mechanical action of a contacting solid, liquid, or gas. Abrasive wear can be erosive, grinding, or gouging. Adhesive wear can be dynamic or static. Contact stress fatigue can be subsurface origin, surface origin, subcase origin, or cavitation pitting. Corrosive wear is the combination of corrosion and wear. Lubrication. The one important means of reducing the rate of wear and the failures due to wear is lubrication. Most machinery components depend on lubrication to keep wear rates within acceptable limits. However, even with lubrication, wear still occurs. The wear process may be mild, but it generates a fine debris of particles as small as 1 or 2 microns. Under lubricated conditions, abrasive wear predominates. Several basic lubrication modes exist. Anyone engaged in analyzing and correcting wear failures should understand all of them. Hydrodynamic, hydrostatic, elastodynamic, dry film, boundary lubrication, and thin film. In all these lubrication modes, the contact surfaces are separated by a lubricating medium. The lubricant may be a solid, a semi-solid, a pressurized liquid, or a gaseous film. In hydrodynamic lubrication, the shape and relative motion of the sliding surfaces cause the formation of a fluid film. The hydrodynamic film is developed in a series of steps during startup of the machine. In hydrostatic lubrication, the lubricant is supplied under sufficient external pressure to separate the opposing surfaces by a fluid film. The surfaces ride on a relatively thick film of lubricant. Elastodynamic lubrication is a system in which the friction and film thickness are determined by the elastic properties of the two bodies in relative motion. In dry film lubrication, a coating of solid lubricant separates the opposing surfaces. The lubricant itself wears away. In boundary lubrication, each surface is covered by a chemically bonded fluid or semi-solid film. The film may or may not serve to separate the opposing surfaces. Thin film lubrication is similar to boundary lubrication in that friction and wear are affected by the properties of the lubricant. In thin film lubrication, the lubricant is usually not bonded to the surfaces and does serve to separate them. Almost any surface film acts as a lubricant. The film prevents cold welding of asperities. The opposing surfaces can slide across one another at lower frictional force. The lubricant may be either liquid or solid, or on some occasions gas. One of the very important functions of a lubricant is to carry away the heat generated by the two surfaces sliding across each other under contact pressure. Liquid lubricants dissipate heat better than solid or semi-fluid lubricants. In all types of lubricants, the shear properties are critical to performance. Lubricating oils are relatively free-flowing organic substances that lower the coefficient of friction in mechanical devices. In general, lubricating substances that are fluid at 68 degrees Fahrenheit are termed oils. Lubricating substances that are solid or semi-fluid at 68 degrees are termed greases. There are three types of oils: oils derived from petroleum, which are essentially mineral oils; oils derived from plants or animals, these are called fixed oils; and there are synthetic oils. ASTM defines a lubricating grease as a semi-fluid product consisting of a dispersion of a thickening agent in a liquid lubricant. In more practical terms, most greases are stabilized mixtures of mineral oil and metallic soap. The soap is usually a calcium, sodium, or lithium compound. There are many types of solid lubricants. Among them are many solid organic and inorganic compounds, as well as certain composite materials. Graphite is a widely used solid lubricant, as is molybdenum disulfide and Teflon. Solid lubricants are generally used for their good stability. They usually retain their lubricity at elevated temperatures, in chemically active environments, and under exposure to nuclear radiation. Solid lubricants also provide certain advantages in high vacuum, aerospace, or cryogenic applications where liquids normally evaporate or congeal. Lubricant failures. When a lubricant fails, the machine can fail. Most failures of lubricating oils and greases occur by chemical decomposition, contamination, or changes in properties from exposure to elevated temperatures. A loss of film can occur from inadequate flow of the lubricant into required areas. Any one of these factors can cause lubricants to fail, but in most situations, chemical decomposition, contamination, and temperature are all involved, and all are interrelated. In general, solid film lubricants fail by the mechanical removal of microscopically thin layers. This mechanical process of removing layers of film eventually causes a lack of dynamic stability, resulting in too much clearance in a bearing, for instance, or adhesive wear of metallic contact surfaces. The common cause of lubricant failure is contamination. Contamination of the lubricant with water or chemicals can lead to lubricant decomposition, corrosion of contact surfaces, or both. Contamination with abrasive substances or debris can cause abrasive wear, especially when the size of the contaminant particles is about the same as the thickness of the lubricating film. Very often, the failure of a lubricant can be traced to the selection of an inappropriate lubricant. Petroleum lubricating oils are available in a tremendous variety of formulations, and often certain oil additives impart entirely new performance characteristics to the base oil. Selection of the proper lubricant is very important. In many instances, lubricant failures and the subsequent component failures can be prevented or corrected by changes in the design of the device or in the design of the lubrication system. An inadequate flow of lubricant can easily starve a bearing. One reason for inadequate flow might be a clogging of oil passages, and this problem can sometimes be corrected by increasing the size of the passages. Often an increase or decrease in the clearance between the sliding surfaces will enable the lubricant to function more effectively. Actually, the single most common cause of wear failures is oil starvation. This is often called dry startup, since it usually occurs at the startup of machinery operation. The conditions of non-lubricated wear are difficult to define. When a lubricant is absent, the process of wear is characterized by metal adhesion and cold welding. In most situations, however, some kind of lubricant will exist on the sliding or rolling surfaces. This lubricant may be only an oxide, but it is still effective. Even surface contaminants may provide a form of lubrication. At least they can prevent the intimate contact of the sliding or rolling members. Metal surfaces are truly non-lubricated only when they are kept in a hard vacuum environment, cleaned by an electron beam or electric arc. Under these conditions, cold welding of the surfaces can take place upon contact. Cold welding can also occur when the contaminating films are penetrated by high pressure. If the asperity junction is stronger than the weaker of the two metals in contact, sliding motion will cause subsurface shear of the junction. With subsurface shear, a particle larger than the junction will be torn from the surface. The junction might not shear off, but it will grow until a critical size is reached. At that point, the heavily worked junction breaks off. This process is known as prow formation. It is found under point contact conditions involving a hard metal sliding on a softer metal. Summary: lubrication. The various modes of lubrication are hydrodynamic, hydrostatic, elastodynamic, dry film, boundary, and thin film. Types of lubricants: lubricating oils, petroleum-based, fixed, and synthetic. Lubricating grease, and solid lubricants. Lubricant failures that lead to wear: chemical decomposition, contamination, changes in properties, and loss of film by inadequate flow. Analyzing wear failures. An accurate analysis of a wear failure depends largely upon evidence from three sources: the worn surfaces, the operating environment, and the wear debris. Surface damage can range from polished or burnished conditions to the removal of a relatively large volume of material. Examination of the worn surface can provide a great deal of information: the amount of material removed, the type of damage, which could be scratching, gouging, plowing, adhesion, pitting, corrosion, spalling, or simple penetration. The existence and character of surface films. The worn surface may also show if certain constituents are being attacked preferentially. The direction of relative motion between worn surface and abrading particles. Whether abrading particles have become embedded in the surface. Environmental conditions also contribute to failure. The conditions greatly affect the mechanism and rate of metal removal. Detailed knowledge of environmental conditions should always be sought. Wear environments may be corrosive. The environments may have been altered during service. The lubrication the environments provide may be inadequate, and they may differ from the environments that were assumed when the original lubricant selection was made. Wear debris can provide clues to the wear mechanisms involved with the failure. The debris can be found between the worn surfaces, embedded in a surface, suspended in lubricant, or beside the worn part. Examine the particle. If the center is metallic and the surface covered with oxide, the particle was probably detached from the worn surface by abrasive or adhesive wear, then subsequently oxidized by exposure to the environment. On the other hand, if a small wear particle consists solely of oxide, it could well be a chip of original corrosion product mechanically removed from the worn surface. The analysis procedure. The conditions leading to failure can vary greatly. Conducting the analysis generally follows these steps. Identify the actual materials in the worn part. Identify the environment, the abrasive wear debris, and the lubricant. Identify the mechanism of wear: abrasive, adhesive, corrosive, or contact stress fatigue. Look for signs of a combination of mechanisms. Define the surface configuration of both the worn surface and the original surface. Define the relative motions between the parts in the system. Define direction and velocity of the motion. Define the force or pressure between the mating surfaces or between the worn surface and the wear environment. This should be done on both macroscopic and microscopic scales. Define the wear rate. Define the coefficient of friction. Define the type of lubricant and its effectiveness. Is it oil, grease, surface film, naturally occurring oxide layer, absorbed film, or other? Establish whether the observed wear is normal or abnormal for the particular application. The last step, of course, is to devise a solution if required. Solving wear problems. In most instances, wear problems are solved by either of two approaches. We can alter the service conditions or change the materials. Both of these solutions are necessarily long-term, basically not really preventive. Wear takes place over a period of time, and in most instances, the actual failure is neither sudden nor catastrophic. Seldom does the part suddenly cease to function properly. So the best solution to the problem is simply to modify. The service conditions may be altered to provide a less destructive environment. The lubricants can be changed. An oil filter and cooler might be added. The vibration of the machine could be reduced in some way. We might modify the maintenance routine by stepping up the intervals of oil change. The other way to fight wear is to change the materials that are wearing. That is, select more wear-resistant materials for the specific operating conditions. Since wear failures are generally the result of relatively long time exposure, the service conditions over the entire period of operation are vital to the investigation. Many of the determining factors require both macroscopic and microscopic examination, and any information obtained at the time the failure is discovered can be very useful in establishing the cause. For example, samples of the environment are taken at the time of failure. Samples of the lubricant are taken, along with sludge from the lubricating system. A used oil filter is taken. All these samples collected at the time of failure can be analyzed later, revealing the nature and the amount of wear debris or abrasive in the system at the time of failure. The examination of a worn part generally begins with visual observation and a measurement of dimensions. This usually requires micrometers, calipers, and standard or special gauges. Observations of the amount and character of surface damage must often be made on a microscopic scale. An optical comparator, toolmaker's microscope, a recording profilometer, or other fine-scale measuring device may be required to adequately assess the amount of damage that has occurred. During abrasive wear, material is lost from parts. During adhesive wear, material is transferred to an opposing surface. Weighing a worn component or assembly and comparing its weight with the weight of an unused part can help define the amount of material lost. The abrasive or wear debris can be strained to determine the sizes and shapes of the various particles. A chemical analysis of the particles will frequently identify their source and the mode by which they were formed. To understand the various wear mechanisms that may be involved with the failure, we can use microscopy and metallography to study the surface features and the microstructure of the underlying material. These procedures are greatly enhanced by sectioning the specimens at an angle. This is taper sectioning and serves to expand the very thin and critical surface layers involved. Etchants used to prepare specimens for the examination of microstructure will also reveal the characteristics of worn surfaces. Etching a worn surface can reveal the phase transformations caused by localized adhesion to an opposing surface. Etching can reveal the results of overheating caused by excessive friction. For instance, the white layer of untempered martensite that sometimes develops on steel or cast iron under conditions of heavy sliding contact. Etching a worn surface can also help in detecting the selective removal of specific constituents in the microstructure. It is also very important that the worn surface be examined under the microscope and photographed before it is etched. Very often, some of the topographic features are easier to observe on the unetched surface. Macroscopic and microscopic hardness testing indicate the resistance of a material to abrasive wear. Harder materials are likely to cut or scratch softer materials, so comparative hardness of two sliding surfaces may be important. Micro-hardness measurements on martensitic steels may indicate that frictional heat has over-tempered the steel. When used in conjunction with a tempering curve, plotting hardness to tempering temperature, the micro-hardness measurements can allow a rough estimate of surface temperature. Hardness measurements can also indicate whether or not a worn part was heat-treated correctly. X-ray and electron diffraction analyses disclose the structure of a crystalline solid. These techniques are particularly valuable for analyzing abrasives, wear debris, and surface films. They can identify not merely elements, but compounds as well. When devising solutions to most wear problems, it is good to know the actual compositions of the worn material, the wear debris, the abrasive, and the surface film. An analysis of the lubricant can determine if the proper base stock and additives were present. Chemical analysis may be needed to establish or confirm the wear mechanism. The microstructural heterogeneity of a wear surface influences the wear process because hard constituents, such as carbides, inclusions, and intermetallic compounds, have properties different from those of the matrix. If they are closely spaced in a relatively hard matrix, the hard microconstituents make a metal extremely resistant to abrasive wear. Matrix hardness is important to wear resistance. If hard microconstituents are dispersed widely in a matrix that is not hard enough to have good wear resistance of its own, the matrix may wear away rapidly, leaving the hard particles projecting from the surface. Projecting particles can cut into a mating surface. For this reason, a fine pearlite matrix under dry sliding conditions exhibits considerably better wear resistance than coarse pearlite or a mixture of ferrite and pearlite. Because wear is a surface phenomenon, the original surface configuration of the components in contact influences wear by influencing the resistance to relative motion. Changes in surface configuration that occur during the wear process affect subsequent stages of wear. An example of this is the process of wearing in. Wearing in a car or new machine serves to reduce the initial surface roughness of the parts, resulting in a long period of minimum wear to follow. When only unidirectional sliding is involved, scratches or gouges produced on the worn surface are aligned with the direction of relative motion. For example, in a sleeve bearing, the scratches should run circumferentially on the inner surface of the bearing and on the mating shaft. Scratches resulting from wear that are oriented in other directions indicate misalignment, vibration, or looseness. These factors can contribute to the severity of the wear. Wear rates are most commonly evaluated when the objective of the failure analysis is to improve the service life of parts. Wear testing may be required to determine if the observed wear rate is normal for the application. Wear tests are generally less accurate and less reliable than tests of other engineering properties. Since there is no universal test for wear, wear is evaluated by many different procedures. Each procedure is designed to evaluate a specific type of wear or mechanism. A wear test is considered a good engineering evaluation if it is reliable, able to rank materials, and valid. A reliable wear test can produce wear on a certain material in a predictable and statistically significant manner. The ability to rank materials includes achieving statistically significant differences in wear rates among different types of materials. Finally, a valid wear test can predict the service performance of a given material. As a rule, wear tests made in the laboratory have limited value. They are merely preliminary screening evaluations and are frequently misleading when used for material selection. Generally, the substance controlling the actual wear in service is the hardest substance in an abrasive mixture. Therefore, the wear tests should accurately simulate the hardness and the particle size of the specific abrasive in the environment that controls the wear in service. Wear tests should also simulate the contact pressures between components. These are the forces that cause contact between the abrasive particles and the wear surface. The test should have the same relative motion between the abrasive and the wear surfaces. Service testing represents the ultimate evaluation of wear resistance. Unfortunately, most service situations are subject to a great variety of conditions. Finding a single material that is best for a given wear application may be impossible.